Isothermal, let's do reversible. Okay, so I've got to stick every one of these, and I'm going to think out loud, because that's what you need to do, not out loud. At the exam, you got to think. And look at this, and all right, let's just break down every possibility. And all right, it may be a little bit messy, but by definition, I've got this. I'll try to remember units. If I screw up units, don't fault me on that one, all right? That's not that big a deal. Worth a point, all right? So anyway, that one's obvious. All right, now what have I got? Okay, what's the basement? Basement is U. Now I need to figure out delta U, but I'm gonna have to start with U. If I know what U is, I can figure out the change in U. And U is one of the things you need to start by, 1/2 RT times degrees of freedom. Now this is a first test thing, but unfortunately tests 1 and 2 are comprehensive. I don't mean them to be. There's no way that they're not. It's impossible that they're not. And therefore, change in U, 1/2, well, a bunch of stuff. The only thing that can change is T. I can't relate the change in U to a change in 1/2 or a constant, and therefore the change in U is 0. Now I'll remember units again. T doesn't change, U doesn't change. Okay. Now the change in U is the change in work and the change in heat on the cheat sheet, but I mean that's the exact nature. See, if this wasn't true, change in U and Q each by their own are inexact and path dependent, but they cancel out each other's path dependence to result in something that's path independent. I always thought that was kind of neat. I still don't get how it does that, but it does do it. Okay, and therefore, the change in heat is minus the change in work, and I'm putting it that way because I know that work is the thing I can calculate. All right, now, okay, so this is how I figure out heat, so I'm done with that. I got to do work. Here's one of the things I have memorized, or more accurately, I remember to look in the cheat sheet. Minus P exterior dV. But by definition, the exterior pressure is held at the interior pressure. Remember, there's no subscript for interior pressure. And this is then equal to PdV. Which is nRT. Now I could insert a real gas equation, and depending on the nature of the real gas equation, that could be really horrible. Depending on whether if there's like an e to the v over v minus b, that it's integratable, but this is too hard. So I got to remember that minus. That's all for the exam. I didn't make a mistake. You can hate on, actually folks, if I carried through and made a mistake, you don't want this one off, right? You want me to screw up delta S, not delta W, right? Right. Pick your battles, folks. Yeah. That's me talking too quickly. So I integrate this, and I remember what the integral of 1 over x is. And like on this homework, I'm really concentrating on definite integrals right now, which is what made your number 4 such a nightmare to do. I realize that. And in terms of asking questions on the homework related to number 4, which during office hours was the one everyone hated, which is integrating the Max V Gibbs Helmholtz equation. That is on the test, but I don't actually have you do any operations. It's like true and false. Anyway, okay, so I've got the change in work. The change in heat is minus that. Okay, now I'm almost, I guess I'm only halfway there actually. I guess I need to do H, which is a Legendre transform on U, where I subtract out the thing I don't like its dependence on times its conjugate. The conjugate of V is minus P, so this is U plus PV. Okay, this is H, not the change in H, so I've got to remind, so I've got to do the change. And, oops, almost, there we go. Change in H is the change in U plus the change in PV. Okay, and this is 0. So this is the change in PV. And now, this is a real nightmare because change in two things that are changing. I can't, isothermal or not, See, if this is isothermal, I could just take the change in T out, right? If there was like a TV, I could just take the T out. But it's not. P and V are naturally going to change, and that would make this really extraordinarily difficult, except that I got a PV equals nRT. I've got this relationship. Again, I've inserted the perfect gas law. Again, I could have not done that. I could have used a real gas equation. It just would have unnecessarily made this very difficult, but this is still 0. The change in T is still 0, so there you go. Okay, now it leaves the bear in the room is entropy. And that's what you want me to screw up. So, okay, now actually I've got 1. I've got the total, and that is 0 joules per K. And that's by definition. By definition of being reversible. And I guess I got to start by that. And that is equal to the change in the system plus the change in the surroundings. And I do have you, the hard one has it on there. And it is on true and false as well. So here I got it therefore. The change in the surroundings, yeah, this is on the exam, is minus that of the system. And this is going to change when I do irreversible, but for now, for reversible, this is exactly correct. So now all I got to do is get change in S, and then I got A and G. So I've actually I've made good progress, all right? One little minus I almost drew up, right? So, okay, what am I doing? I got to do change in S. Change in S, which is the change in reversible heat over temperature, which happens to be the change in work. I'm going to write a little reversible. I don't need to because I'm doing a reversible problem, which is minus minus plus nRT dV over TV. nRT over V, then I have to write, so the T's cancel. So this is nR changing V over V. And then, of course, delta S is the integral of the partial, which is the integral nR dV over V dI dF. And this is the big nR ln dF over VI. Okay, and then the surroundings is minus that. Check the units. R is joules per K per mole times moles is joules per K. Natural logs do not have units, as we talked about several times. Everything's fine, so that just leaves me A and G, and I do, enough is rattling around in my own noggin that I remember that A and G I'm going to be able to come up. So if I ask an isothermal on the harder, gas expands, gas contracts, I should be able to ask for A and G on that one. I can't on the adiabatic, and I am going to cover that. Okay, regardless. Okay, so let's do A. That's the first one I introduced, which is subtracting away S times its conjugate. So that U is a function of S, but I don't like that because that's difficult. So I've subtracted out its U's dependence. And therefore the change in A is the change in U, which is 0, minus the change in TS. Okay, so now this is where things can get really hairy. Now when I was doing H, and I had this change in two things multiplied, I had an out. I was able to turn that into a bunch of constants times T, which can change. More accurately, it wasn't, so it ended up being 0. But the problem I have here is that I don't have a perfect gas law with TS now. I don't have a TS equals nRT over V, or you get my point. I got no good outs with this. So what I might want to do, how do I want to do this? Okay, I'm going to try this. And, yeah, I do have this one memorized. TDS minus PDV minus TDS minus SDT. Okay, that's gone. Minus PDV minus SDT. Okay, but minus SDT, but T is constant, so this is reversible work. Okay, so I can just plug in my formula for reversible work, minus PdV, the P is the interior pressure. Okay, and then what I'm going to get with G is the change in H minus the change in TS. Given that this is 0, I've already proved that, I've got the same thing minus TS, but I'm going to run into the same problem, and I'm just going to find that that is also the reversible work. I'm going to show that too. All right, but unfortunately there are actually multiple ways to do this, and you might want to know about this other way. All right, so again, nuts and bolts, the magic cylinder, gas expands and gas contracts. Did I ask A and G if it's isothermal? Yes, now you know how to do it. But let me give you another way in case it appears in the easier question. Okay, let's go back to A. Change in U minus the change in TS. See, if you really know what you're doing, this is still 0. You actually, I showed you this when I introduced this, but it was a real bear. I made it a little overly complicated. I can do this. I can do TDS minus SDT. I am actually able to do that, but T is still constant, so this is minus TDS. Right? And so in G, we'll do the exact same thing. Yeah, I'll just remind you of that. So I have another way to calculate delta A, or delta A is delta G, because I've established that if I go through this exercise with G, I'm just going to have an H there, and then it's all the same, right? And so what this ends up being is minus T delta S. Both of them would be minus T delta S, which actually would be the same as reversible work, because that's actually how I calculated S, was inserting minus the reversible work over T, so I put in the minus times T. That all makes sense. These will be the same answer. And another way I know that this is right is because I have a T. I have a T here. If this was an adiabatic and I derived this, I couldn't be right, because T is changing. But it's isothermal. T is not changing. The fact that there's just a T here makes sense to me, because it's static. S is changing. I already know the formula, so it makes sense that there's a delta S. I know I did it right. How'd I do? Am I done? Okay, I guess that's the main thing, so I covered everything. Done.
More stuff here.
What was that?
You even did, like, you derived it more here than here.
Well, yeah, I did a little. Oh, wait. No, I did the surroundings. Yeah, I did. Yeah, all right. Okay. Let's go again. So I'm going to actually end a little early because adiabatic, irreversible is actually going to be very, very similar. Irreversible is very similar. I've just got an entropy. I'm not even going to spend much time on this one because the isothermal, I want you to have the same knee-jerk reaction to isothermal that I'm going to have, because I'm not going to just rewrite all the change in U's and H's again, because that's kind of stupid. Maybe we'll get out a little early for the first time. So let's get rid of reversible and do irreversible. Okay, so change in T is 0. Remember that if I ask that, I will put change in T as the first question. It's a 3-point. And for all the same reasons I've just covered, change in U is the change in H is 0 joules. Again, I'm not going to go over that. The change in heat is still going to be minus the change in work. Okay, but this is where I'm going to find my first difference. I'm going to go with my definition of work. I'm going to use the partial form. And remember, by definition, you have a constant external pressure, so there's actually not much to do. So to get a big delta change in work, I've just got this. And the only tricky thing will be that I've snarkily given you the exterior pressure by giving you moles, moles will always stay constant. I gave you the final temperature, final volume. So that would have given you the exterior pressure. You know all the tricky ways you can hide variables in PD Biz and RT questions. So that's the only part that could be a little tricky. Okay, that's work, heat, all the U's and H's. I don't, in terms of like first test things, I don't think I've forgotten anything. What do I want to do now? Okay, I guess I need to hit entropy. So why don't I actually start with the total is simply going to be greater than 0 by definition. Okay, so Dambo, there's a point. There's not much else. One of the things you got to remember, I try to minimize that, but I can't do it perfectly. But this is still, therefore, the change in the system plus the change in the surroundings has to be greater than 0, which means that the surroundings simply has to be greater than, this is just straight algebra, greater than minus the change of the system. And remember, you can logically walk your way through that. The one that could be truly tricky is a negative, a compression, a negative delta S in the system. And so let's say it's minus 5 joules per K. You got to remember that the outside would have to be greater than 5, not greater than minus 5, because the net would be just slightly less than negative 10, and then that's wrong. So again, a minus compressive change in S would be negative, so let's say it's minus 5. So that means the outside has to wipe that out, has to be 5 plus a little bit more, so greater than 5 joules per K. So that's how I walk through that to make sure I've done it right. Okay, now S itself, so basically I've gotten that, and if you got this, I would probably just go ahead and give you full credit. S, this is where it gets a little funky, being an exact differential is still the reversible heat. Even though this is an irreversible problem, it is still reversible. And therefore, the delta S is NRL. I'm going to get the same thing. And I'm not going to bother to derive it because there you go. Yeah, I mean, all I would need to do is start rederiving reversible heat as minus reversible work. Minus reversible work is nRT LCM over VI divided by T. There you go. Okay, so that leaves the A, which is still EG, which being exact differentials, this is still going to be the reversible work. And it will still be T delta S, minus T delta S. There's no reason for that to change at all, and because they're exact, just like before, all my exact variables are the same. A and G are still the reversible work. I'm sorry, I should say delta A, delta G. Now I'm being able to be right. Integrate them. So you integrate them, you get this. Those are the exact same. The U's and H's are the exact same, reversible or irreversible, because it should be that's path independent. S should be path independent as a state variable. That is indeed the same. Work and heat are not, and sure enough, they're not. Work, we've shown you that reversible and irreversible work are not the same. Again, this is the first test thing, and heat was just minus that. Did I get it? Did I cover everything? Oh, okay. All right, move on. I feel like I was skipping something. Okay, now this is the painful one. Actually, the adiabatic, which is really a very odd condition. It does describe refrigerators, and refrigerators are things that people care about. But it's kind of adiabatic systems are really, I think, best for testing your understanding of this stuff. And I've been a little tricky on true and false, talking about adiabatic and entropy. Remember, adiabatic is good for really testing your knowledge of stuff. So in terms of adiabatic conditions, I don't think I've asked a question like a derive dP dV at constant S. Remember those that were kind of, they were a little bit at the harder end. I did not ask one of those, but I had asked you to describe one. I just said that a little while ago. And let's see, I've also been a little snarky with remembering that adiabatic reversible means that the total change in entropy, that the system entropy is 0. Let me just start writing. Let me just start writing what these relationships are. And I got to remember, the first thing I need to put down is that dq is 0. That's by definition. So remember, this is it's defined that way, so that gets a star, but hopefully nothing else. And now, you know what? Now I'm stuck, because the next thing I normally need to go for is U. And U is going to change because temperature is changing. So remember, the equipartition theorem says U basically only changes with temperature, but now Bisnacker temperature is changing. Okay, so that's a real pain. And even though this is on the test, last time I got to remember this little graph. It's going to be T and V, and the change in U1 is 0, change in U2 is CV dt. Okay, so the change in U is the change in work. By this little graph, this is CV dt, but by the change in reversible work, is PdV, which is nRT dV over V. So I see I'm going to have some natural logs. Okay, so minus, yes. I knew that. I got it. Okay, so minus CV over nR dt over T is dV over V. Okay, and what I'm really doing here is I'm just trying to get to delta T. What I've got, just do a little bit of, I'm not going to go through the whole thing because it's kind of stupid. It was a first test thing. I'm going to have a VF over VI. I'm going to have a TI over TF. Those switch because of the minus sign. The CV over NR. Okay. Again, actually a first test thing, but if I have a reversible adiabatic, then you do need to have that. And again, it would be on the cheat sheet. I will send it right after this, especially after the homework's grown up. I will send it to you immediately. All right, what I get from there is delta T, and so now I know that delta U is CV delta T, which you just put in as the change in work. Don't forget that. If you don't write it down, even if you just do this, plug in a number and say that's change in work, you got full credit. It's just that when people just simply forget to just give me something, actually, like okay, you've turned in the test, the hard question, and I don't see something like this, I'm going to scan your entire thing for I'm looking for the letter W, and if I see it, then you're getting a point. But when you just completely ignore it because of relationships like this, that's a point loss, so try not to do that. Okay, I've got this. Okay, let's do the change in H. And I'll put this in delta form, which is delta U plus NR delta T, which is CV delta T plus NR delta T. And I recognize that this is CV plus NR delta T, which is CP delta T. So U is CV delta T, delta H is CP delta T. Or this, if I don't happen to explicitly state what CP is. I'm not going to insert real gas behavior in this stuff because it's if I insert real gas behavior like here, that would just be, I mean, I'm sure you could get it, you know, even if you just used a computer to solve the integrals. But I don't really see the value in that other than just throwing hard questions at you for the hell of it. So I'm not going to do that. So this is a perfect gas result. We've actually solved that, but that will be fine. I'm not going to insert real gas behavior here. Okay, so that's work H. I guess I got to get to entropy in A. Is that what I need to do? Am I forgetting something? The heat. Yeah, I've got entropy A and G left, right? Okay, all right, well, I'm making good progress. And by the way, as you hear me say anything that's not related to this kind of test one stuff, that's me dropping hint because, again, I wrote the test. I know exactly what's on it. It's swimming in my head in a big, big way. So just pay attention to that. Okay, so now I've got adiabatic reversible. I've just got the last variables to go over. And I'm going to start with entropy, and delta S total will be 0 joules per K by definition. Okay, so I don't think I had that in the cheat sheet, but that's really not that hard. And this is, of course, delta S of the system plus delta S of the surroundings. But this is 0 by definition because there's no heat exchange. So I've got two definitions, and that therefore this has to be 0 joules per K. Really no option on that. 0 is equal to what plus 0? Well, you're left with 0. Okay, so those are the entropies. So that's what's special about adiabatic is adiabatic reversible is a very special one. As much as I think your average engine is probably irreversible isothermal, because that's like the nastiest machine ever, would be an isothermal irreversible one. This is a perfect little Primrose, kitten wearing a bow tie type of engine. And this is why it's special because of this property. So you might want to look out for, remember that if I say something is adiabatic and reversible, and outside of the context of a magic cylinder question, then what I'm really trying to get you to remember is this, that this is the case. So you can imagine like change in U. Remember, change in U is special if entropy is held constant and volume is held constant. And you think, well, how would you ever do that? You know, I understand that constant volume process is just a process in a metal sphere, you know, a metal magic cylinder that's jammed. Yeah, just a sealed container that's strong, that's constant volume. Constant entropy would be done under adiabatic reversible conditions. And there you go. Anyway, all right, so now I've got, okay, the real painful one. Now remember, I cannot ask you change in A, change in G on the adiabatic ones because of the following problem, which is that I'll do A, is the change in U. Sorry, my writing is off the wall. Minus the change in TS. What's wrong with me? Sorry. I'm still disturbed I left her homework sitting on my desk. CV, DT, that really bothers me. I'm sorry about that. Minus the change in TS. Okay, so here we get stuck again. We get badly stuck. I've got the first CV, DT. All right, that's not hard. You've already done it. I've given you CV, but I got this change in TS. I got no way out on this because, again, I do not have a perfect gas thing to turn. You know, two things changing simultaneously is just simply way too hard. And let's see here. So let me try that trick I tried before. Minus TDS minus SDT. Well, that really doesn't work. That utterly doesn't work. Wait. No, hold on. Look at that. No, hold on. Yeah, look, I could eliminate a term, right? The change in system entropy is 0. So it looks like I can make progress on this, right? So therefore, I'm going to insert a mistake. Let me insert a mistake. Because I might have you do something like this on the test. Okay, is that right? Sorry, I got to break character for 1 second. I'm not Stephen Colbert anymore. Is that right? Looks okay. I mean, I got, like I say, it looks like a nightmare because I have two things, but the delta S is 0. System entropy 0. So I just integrated DT. Yeah, S has a T inside of it, right? Remember, and that's KLN number of microstates, but the problem is that number of microstates, which, you know, chessboard, there is a question. It's actually cats in a bag. I do have an entropy question with KLN microstates, by the way. It's in the form of cat in a hat, cat in a bed or something anyway. It's the extra credit question. There's a T inside of it. There's a T inside of it, you can't, and you really cannot ignore that. Some things like on the homework, The answer to the question is that heat capacity is also temperature dependent, but it's very weakly temperature dependent. Entropy is massively temperature dependent. It changes a heck of a lot with temperature. You cannot ignore that. All right, you can, you're just going to be dead wrong. So what you have to do is, model S as a function of T, and then use Wolfram, like, use Mathematica to actually solve it on a computer, which is something I actually really would want you to start doing. I actually try to get you to use computers as much as possible, because that's just how things are. I mean, this course was designed in the 1950s when no one had a computer, and it just hasn't changed, and that's really crazy. So this is doable. I'm not trying to say it's not doable. It's just you're going to need a computer to do it, and unfortunately, historically, we just don't ask you to do that. And then changing G is the same thing, minus changing TS, which again is unresolvable. Okay? Guys do anything? Okay, last but not least.
Well, you wrote for delta, or for changing G, it's CP delta, CP.
Right. Sorry, this is for CP. DT. Oh, okay. I'll take it off the test. All right, I screwed up. All right, off the test.
Yeah. It's not him, man.
It probably wasn't on there.
Yeah, it probably wasn't on there.
I still lived up to my word. I'm not going to say anything more. Yeah, you got me. And I lived up to my word. I won't have it on the test.
So do you replace it with another question?
Just trust me. Maybe I don't need to do anything. Because I can't query you on that with an adiabatic question, right? Remember, there's only 2 calculator questions. I will bring a calculator. All right. Let's do this, folks. Come on, we're almost done. Almost done. Let's do adiabatic irreversible. By the way, there's a trick to this one. I haven't ever gone over this, but this is really important. There's actually a trick to adiabatic irreversible that I have not covered. It has to do with entropy. All right, well, let's just knock through the simple ones. By definition, adiabatic is by definition, there's no heat exchange. Change in U will be CV delta T minus, it's going to be equal to minus exterior dV, and therefore the point of this is to get to the change in temperature. And as you are well aware, this is as far as I can get because the exterior pressure is constant and it looks all nice and easy. It could be easy if I simply fed you more information, but you know I'm not planning to do that. And this question ends up being a nightmare. Actually, significantly harder than the adiabatic reversible with a rather simple adiabatic reversible equation of state. This is how you calculate delta T, but due to the complexity of algebra, this actually ends up being significantly harder. Regardless, now you've got the change in work, which is the change in U, which is CV delta T. By the same logical derivation, change in H will be CP delta T. And again, that can't change from what I just did. I'm not going to rederive it all because they're state functions. They have to be the same. And likewise, let's see, use H's. Delta A is going to be CV delta T minus delta TS, which is unresolvable. Change in G is CP, and got burden on that, minus delta TS. Again, unresolvable, same problem. And last, that leads to entropy. And this one is a bisnogger. Let me do the total. Let's see, delta S total will be greater than 0 joules per K by definition. This is the definition of an irreversible transition. And it's equal to delta S total is delta S of the system plus delta S of the surroundings. But that's still 0 because it's adiabatic. And therefore the total is the change in the system And this is where I'll leave you, actually. Let me get a new board. Because I actually glossed this over. I know you know what the formula is, and it's on the cheat sheet. The CP ln TF over TI, NR ln VF over VI. I know you know that, but I actually kind of glossed over that derivation because I kind of forgot to do it. But let me point out something very strange about this guy, which is that entropy is the change in reversible heat over temperature. Already I've got a problem because temperature is changing, but I even got a bigger problem because there's no heat. So it looks like it's 0. Is it 0?
1.
It's not 1. It's not 0 either. You see, this is actually a historical mistake. Entropy was defined this way because it almost always works. But see, none of you are, I don't think any of you are engineers. See, you need to tack on plus entropy added. You see, this is actually incorrect. This is historically how we write this, and it's a historical mistake. Just like Benjamin Franklin thought electrons were positive, so if any of you know electronics, you actually analyze circuitry in reverse. Because they used to think that electrons were positive, and it became a historical mistake that's carried through to this day. This is a historical mistake. We still define it this way, but engineers who actually got it right say that there's another term. Entropy added is what they call it. But anyway, because if I use this, it's 0, and it's not 0, it wouldn't be irreversible because of the logic I just showed. Okay, so the way you actually solve this is that you realize that this equation is actually wrong, and what I'm going to do is expand it in the way that is on the test. I mean, just in general, you know, functions. You know, I like functions. So I'm going to do it this way. Okay, now this guy, I'm gonna actually use. I'm going to use this. I'm going to say this is. Sorry for the aside. I'm kind of running out of time. ds is dq over t, which is cv dt over t. So what I've got is cv dt over t. See, I'm going to see my natural log, CV natural log t over ti. But now I got this one. Maxwell equation. You do need to use a Maxwell equation in the hard derivation. It's a du dv at constant t type thing, and then there's a real gas law. You're going to need a Maxwell equation. Maxwell equations are on the cheat sheet, including the one you need, but you still need to work it. If you can't derive yourself to the point that you need a Maxwell equation, you don't know what you're doing, which is why I'm testing you. All right, but now here's what I recognize. I have the Maxwell equations on the cheat sheet, but here I have no notes. I've eliminated one from the test, the DG, under AB beta reversible. But I recognize I need a Maxwell equation that comes from an energy function that has V and T in it, which is A. Okay, change in A is minus S dt minus P dv. And I recognize that this is dA dt, constant V dt, plus dA dV at constant T dV. And that this guy is therefore minus S, and this guy is minus P. Now, then what I do is I use Euler's test. I know I called it Euler's criteria. I was actually mistaken about that. To know that the double derivative of this guy is equal to the double derivative of that guy. Sorry, this is a derivative, so one more derivative. The derivative with respect to I've done t, so I do v, and this is s. And now I'm going to cheat ds dv at constant t is, I'm going to cheat now dp minus dp dt at constant v, which is minus nr over v. All right, so what I end up with is, no, minus minus plus. Right, because there's no minus here. Now almost. And what you end up with, therefore, is delta S is nr ln dx over di plus cv ln tf over ti. Is that it? I got it? I did it. Got every one of them. Okay, everyone, sorry.